Okay, we're back again, and today we're going to talk about components and the use of components. We're going to talk about what components are used for, what they do in a circuit. This is going to be a part of how you're going to learn electronics. Again, I know in previous videos I said, I don't want to spoon feed you guys. I want you guys to learn, through your own exploration and your own research. But of course, this channel, like any other channel, is meant to help those and guide you into the process. And I really want you all to succeed, and I don't want you guys to struggle in your search. And I want you to keep the enthusiasm that you have for electronics throughout this journey. So I'm here to help. What I'm going to do today, again, is we're going to go through what these common components are used for. We're just going to go through, 6 basic components. There's 7 components there, but 2 of them are the same. We'll talk about that in a second. But I just want to go through what these components are used for. These are the basic components. And then soon after this video, I'll talk about circuitry and how these components are used in circuitry and what we're going to call typical networks. Okay. So again, as I showed in my previous video, I want to do this because on my previous video, I realized that I might have jumped ahead going into showing you those circuits without giving some explanation on smaller packages of circuitry. What I mean by that is in that last video, I showed you guys kind of how to break down a circuit through stages, looking at different stages of a circuit to break it down so you can understand what's going on in the circuit. But to be able to do that more effectively, you need to know about networks, about RC networks, about networks that circuits are typically comprised of. And to know about networks, you also have to know about what the function of just a simple component is used for. So without further ado, let's get into it. This is the first one we have on top. I hope people recognize this by now. It's a resistor. Okay. This is a resistor. Okay, and then we're going to itemize here the use of a resistor. What's a resistor used for? Okay, we're going to go into, let's talk about AC first. AC current, in terms of AC current, resistors cannot resist AC. Okay? So first thing to put in your head, resistors cannot resist AC. Now I know someone's going to come here and bring up some kind of caveat. Resistors can be used for loading in AC. Okay? There are some uses. I'm not saying there's no use for resistors in AC, but if you're talking about a typical electronic circuit that's going to be using DC power, most of what a resistor is used for is going to be concerning DC power. Okay? So resistors cannot resist AC. They can load AC. They're not efficient at and we'll talk about this later. Again, this is getting to something more complex, but they're not very efficient in resisting AC. Okay? So that's the first thing. So we can say next to that resistors are used primarily for DC circuits. Okay? Resistors are used primarily for DC circuits. Now they're used for what? Resistors resist or drop voltage and current. So resistors can drop voltage or current. Resistors can be used to, so you can say lower voltage or current. Okay, so what that means is at any time in a circuit where you're wanting to have less voltage or less current, you can use a resistor to accomplish that. The most basic component to accomplish that is a resistor. Now again, someone might come in here and say, well, there's a caveat to that. Of course, there's all kinds of ways to manipulate things, And you'll find throughout your electronics journey that you can use other things to manipulate the same kind of things, because as I'm going to talk about in another video, there's this building circuits is a balancing act, okay? And we'll talk about that later. I think in my next video, I'm going to talk about what you balance in electronics. I recognize that a lot of people that are on this channel are actually mechanical engineers wanting to learn more about electronics, which is really cool. And I want to kind of start likening things to mechanical engineering, because you'll find that within every engineering discipline, there's a certain paradigm, there's certain aspects of consideration that you use to make the product that you're making. And electronics is no different. There's like about 4 or 5 things that are primarily what you're concerned about in circuitry to make it work. Just like in mechanical engineering, there's certain things, there's certain parameters that you have that you go, just like in civil engineering, same thing. There's certain parameters that you basically just tick off the list, that you go down the list. Like, did you check the structural strength? Did you check clearances? Did you check tolerances and things like that? Those are the primary considerations that one has when they're building things of that nature. The same thing goes for electrical engineering. Okay, and we'll talk about that in another video, but again, I just want to go over these components. So what we have for resistors is that they cannot resist AC current. Resistors are used primarily for DC circuits. They resist or drop voltage, reduce voltage or current. Now, when I say voltage and current, that means I and V. Okay, if we're looking at Ohm's law stuff, that's I and V that they'll drop. Okay. So, what else is a resistor used for? Quite inversely, we can say resistors are used also to increase voltage and current. And this is something I will go over in one of the next videos that I make involving networks and how components can be used, because you might see that that's counterintuitive. Naturally what resistors do is they're made to resist. That's why they're called resistors. They're made to resist. This is primarily what they do. And they're primarily used to resist in DC circuits, like we talked about. But you can also situate resistors in a way in circuits to be able to increase voltage at that particular node. Okay, when I say increase voltage, if we know a little bit about, Kirchhoff's law and things like that, you can't get any more voltage in something than you already have, than you put into it. Okay, you can't put any more voltage in something on the other end into it. But what I'm talking about when I say increase the voltage, you can increase the voltage at a certain node. Let's say if there's no voltage at a certain node, you can use what's called a pull down resistor to pull energy or electricity or voltage down from another source. Okay, very much, again, if we liken it to another kind of engineering discipline, very much what you might think about when you're talking about civil engineering with compression and tension, right? You can use a rope. You can use something like a rope or some object to cause compression, or you can use it to cause tension, that kind of thing, right? The same kind of idea with the resistor. So it can resist. If a lot of times people like to talk about voltage in terms of maybe some kind of pressure. So you can resist the pressure, or you can use that pressure to pull. Okay, so you have a pull down resistor as well. So that's what a resistor is going to be used for. Okay, so it can reduce our current flow, or it can increase it depending on where we situate it, and it can increase our voltage, or it could decrease our voltage depending where we situate it. Then we have the partner of the resistor, which is the potentiometer. Usually we just call this a pot. It's a potentiometer. Now, a potentiometer, I'll put this a little bit over here because it's both of these symbols. This is why I wanted to do this. You might hear a potentiometer called a variable resistor, and a variable resistor is usually denoted like this over here on the right. But this is more common when you see a potentiometer in a circuit. The reason for that is because it has 3 pins, and in a circuit diagram, when I say in a circuit, I mean in schematic, you'll have the pins denoted on here. So these are numbered 1, 2, and 3. Okay, 1, 2 is in the middle, and then you have 3. Okay, and those are going to be important because that dictates the way your potentiometer is wired dictates its rotation, if you want it to go clockwise or counterclockwise. to increase or decrease. Okay, so that's your potentiometer. So it's a variable resistor. Now potentiometers also have some caveats when it comes to AC and DC. So typically, potentiometers are used for signal attenuation, AC signal attenuation. Okay, that's usually what potentiometers are used for. Now, the reason why I say that is because, so when we're going to talk about potentiometers, think of like a volume control. A volume control is a potentiometer, and what is it doing? It's attenuating the AC signal. Now we have to make a consideration here. There's a difference between AC signal and AC voltage. AC signal, there's no voltage there. There's no like energy. It's just signal. Okay. Now we do measure signal in volts. This is what can kind of get confusing. So let's just talk about this now. We'll talk about this later. There is we do measure signal, like peak to peak signal in voltage, but there's not actual voltage there, meaning that it's not gonna, like, you can touch signal. Like let's say I have a guitar amplifier or a guitar, yeah, either way I have a guitar amplifier or something. You can touch a guitar cable and there's AC signal there, and it's not going to shock you, right? There's no actual voltage, like there's no DC voltage there. There's AC voltage. You can have AC voltage, but that's just in terms of signal. Okay, and then you usually, if you touch like the end of the guitar cable or something, you see that there might be some kind of static or something. But that's because your body is introducing basically its own signal, becoming part of the circuit there, and you might have some grounding effects that makes it speak some kind of way that causes some kind of static, or introducing some kind of radio interference or something like that. But that's the whole idea of that. So when I say AC signal, I'm just talking about signal. I'm sorry. There we go. So I'm just talking about AC signal. Now, potentiometers can also be used for DC voltage. Now, they're not the most efficient things, but in certain, it gets a little bit complicated, but it depends on our impedance, what your impedance is like at a specific point in your circuit. But a potentiometer can be used to attenuate DC voltage. Okay, and the place that you'll see that most often is in like a voltage regulator. Okay, in a voltage regulator, you can have a potentiometer that will change your DC voltage output with a potentiometer. Again, just like resistors, variable resistors are not used for AC voltage. I'll say AC again, AC voltage, not AC signal. They are used for AC signal, primarily used to attenuate AC signal. Secondary function would be to vary DC voltage. They are not used for AC voltage. And that gets a little bit more technical. Maybe one day we'll talk about that. There's something that is used. Now there is something that's used for AC voltage. It's called a rheostat, okay, or a variac. A variac is just an object with a rheostat in it. And the basic function of that, the basic function of a rheostat's basically like a variable. Instead of a variable resistor, it's not using resistance, because again, resistance isn't isn't really capable of really influencing AC signal. Okay, so because of that, we use a rheostat, which is basically a coil, is basically like an inductor that's tapped to where you can increase or decrease the amount of windings on that inductor, and as you increase and decrease the amount of windings that you use on that inductor, that'll increase or decrease the voltage. Because as we talked about in the Tesla coil video, an inductor, like a transformer, which is basically a big inductor, it uses electromagnetism. So we're going to use the principle of electromagnetism to vary the voltage for an AC voltage. But for DC, we can use the potentiometer. Okay. Now, the next we have a capacitor. This is a nonpolar capacitor. Okay, so your nonpolar capacitor. What is your nonpolar capacitor used for? This might get a little hairy too, but we'll just keep going through it. Nonpolar capacitors can pass AC signal. Nonpolar capacitors can pass AC signal. They can influence AC signal like we talked about with low pass and high pass filters. Lots of things that we can do with capacitors to influence the AC signal, but they can pass AC signal. Why is that important when I say they can pass AC signal? Well, just like the resistor, how it has certain things that it appeals to and certain things it doesn't, capacitors are the same way. So what do you think the next thing is going to be? Cannot pass DC. They cannot pass DC. So what's one of the primary uses that you might use a capacitor for? Well, you might use it to get rid of DC voltage. You see, so this is the kind of thing that's going to happen. Now you can start to see what's playing into designing a circuit. Let's say you don't want DC voltage somewhere. Let's say you want to get rid of it completely, right? You have some voltage on one end of the circuit that's needed to be there, but you want to get rid of it at the next stage because whatever the other component is following that is not going to take kindly to that voltage. It doesn't need that voltage. So what do? Well, you could use a resistor in theory, couldn't you? Because you get a big enough resistor, and that resistor is going to decrease that voltage, right? But resistors also, because of the nature of what they do, they actually resist it, right? They resist it. So using a resistor to take away, let's say if I have 100 volts on something and I want to take that voltage to zero, I'm gonna have to have a big resistor, and that resistor is going to get very hot. It's going to do a lot of work, basically. Again, going back to mechanics, going back to engineering, I used to think about this in the same way. All these things are going to do a lot of work because, you know, what is heat? Heat is expended energy, you know, from something that's working. It's expended energy. So we have to expend a lot of energy. We don't want things to get hot, you know, just like in mechanical engineering. I mean, of course, there's some things that, of course, get hot by nature, but you want it to sit at a certain temperature as well, right? It's the same thing with electronics. There's sometimes some things get hot in electronics, and that's fine. If you need to control the temperature, you might put a vent on it. You might put a fan on it. What's most common is you put something called a heat sink on it. Okay, but it's laudable to have because in engineering you have losses, right? So, and losses usually come in some kind of transference of heat. Okay, so that's fine, but you know, we don't have to go through that because guess what? If I use something like a capacitor, which cannot pass a DC voltage at all because of the way it's constructed, you know, capacitor is really like a basic capacitor. Basic capacitors are just made with like a foil ring and then a foil layers and with wax in between them as an insulator. And one end will be able to put in the DC, but the DC won't come out on the other end. The only thing that'll come out is the signal. Okay, the only thing that'll come out is a signal. So this is what a capacitor is going to be used for. It's going to be used for a situation. A nonpolar capacitor is going to be used in a situation where you want to pass your AC signal or manipulate it in some way, meaning like you want to filter it in some way, but you don't want the DC signal. Okay, you want to block. See, so capacitors can be used also as a way of protection when you don't want voltage somewhere. Okay, so that's a primary use of a nonpolar capacitor. It can pass AC signal. It can also influence or attenuate the AC signal in some kind of way, usually in terms of frequency. So we can say change frequency. Change frequency response. I'll say it's not going to change the frequency. It's not like it'll take something, it'll take 100 hertz and then change it to 50 hertz. No, that's not what I mean. It's not going to change the actual frequency. It'll attenuate whatever frequency it's given because it can filter it. It can change the frequency response because it can cut off the corner frequency and all that. Okay. So that's your basic nonpolar capacitor. Now let's talk about your polarized capacitor, what's called a electrolytic capacitor most of the times. So your polar capacitor, what can it do? And this is something we might be a little bit more familiar with. Capacitors, a polar capacitor operates a little bit more like a battery. Just so you can draw the correlation. Why is it like a battery? Because it can store energy. Now this isn't the primary way we use it. This is the way we can use it, and a lot of times circuits are used. Electrolytic capacitors are used in circuits to retain energy, and the reason for that is not because it's trying to use the energy. When I say it's going to use the energy, it's going to use the energy in there for a specific time period. Usually that's very short. Okay, so when I say it's like a battery, usually we use batteries for a long span of time, right? We put a battery in a certain device and we use that as the primary energy source. We're not using a capacitor as an energy source. We're using it to momentarily store a certain volume of energy in it, so it can then discharge it to some area in the circuit when that circuit needs a lot of power, instantaneous power. Okay, so when it needs instantaneous power, we use a capacitor to help out with that. A very good example of that is this is why I said you might be more familiar, even though these are not electrolytic because these are AC. There are AC capacitors that are used in industrial settings for AC, but they're non-polar. Okay, so they relate more to what we're talking about in this first area here, the non-polar. But an AC capacitor, you'll be more familiar with them in air conditions and in ceiling fans, and they are called starting capacitors. Why is that? Well, because what does it take? It takes a lot of power to start a ceiling fan. It takes even more power to start an AC unit. So what that starting capacitor does is it takes that 120 or 250 volts or 240 volts that's introduced to it at the beginning, and it'll charge up that capacitor, and it'll discharge it instantaneously, so there's no lag in the system. So it's easier for the system to handle the load. Okay, so that's what an electrolytic capacitor does. When we talk about electronics, we're going to be doing the same things a lot of the times, just on a smaller scale. Okay, smaller scale, but it's the same principle of using instantaneous power. The other thing we're going to use these things for, this is the primary way we're going to use these, is filtering power. Also filtering power. So again, in the AC world, they're used more for that instantaneous power starting capacity, like I talked to you about. They're also used for smoothing. I can put this here. I can put smoothing because that's part of the kind of lexicon of language that you're going to hear when you're talking about capacitors and electronics. They might call it a smoothing cap. If we're going through and doing a circuit analysis, you might hear, oh, this is the smoothing cap, someone might say. That means it's the filter cap. So we're going to use that usually. So I'll say this. Where is it found? Location. Usually found in power supplies. Okay, so polarized electrolytic capacitors are usually found in power supplies for this reason. If you just go up the list, right? Usually found in power supplies. Why? Because they filter power or smooth the power out and they store electricity. They store energy, which could be useful to the circuit. It could not be. Like I said, not every circuit is so demanding of energy that it needs the capacitor to hold and discharge it and all that. Primarily, they're used to smooth out the AC the DC signal after it's been rectified to AC. When I say rectified, I mean changed into AC, converted into DC. After AC signal's been converted into DC, it usually needs something to smooth it out. So if you're not aware, AC signal can be, we call it dirty, right? It cannot be very clean, right? So we want to smooth it out. We talk about smoothing it out with a capacitor. So that's what happens. This next one, next to last here, we have the diode. Now this can get a little technical, but again, we have to introduce this. We have to talk about it, and we have to get more familiar with these components. Now we're nearing into a more technical component, because the last two, the diode, and after the diode is going to be the transistor, is what we have on the last one, these are the bedrocks of our semiconductors. Okay, so these last two are semiconductors. The first two are just regular components. They're kind of the bedrocks. Resistors and capacitors are the bedrocks of just how you do circuitry, how you manipulate circuitry, how you build circuitry. Okay, main two components for electronics. But then we have our semiconductors, which is a diode, and a transistor, which is basically two diodes put together to make a transistor. To where you have a diode only has two legs, and then a transistor will have three legs. And we'll go into a transistor a little bit. Again, I'll try not to go in too much detail, because we can talk about them ad nauseum in another video. For the length of this video, we can talk about these two components. So I want to just give you a brief overview of this. So a diode, what does it do? It lets current or voltage pass in one direction and not the other. Okay? That's the bedrock, and this is what might be illuminating for some of you guys. This what might be encouraging or interesting for you guys when you see, okay, like, how do things work? And then you realize, wow, that is almost mechanical. That is almost mechanical. Isn't that interesting? Again, a lot of mechies here, a lot of mechanical engineers here, and they're interested in electronics. The diode is often referenced in electronics as a way to illustrate it as a valve. Okay? It's like a valve, which a valve is a mechanical object, right? And what does it do? It lets things flow in one way and not the other, right? The same thing with a diode. A diode is like an electrical valve. This is illuminating, again, because when we talk about physics, when we talk about, well, why is it that everything is correlated? See, electronics is not just some kind of new, different, mysterious world. It's taking everything we do in the physical world and just applying it to electrons. Again, because electronics is just about the management of electron flow. Okay, we're taking electrons, which is energy, and we're just trying to make it flow in some kind of way to make a useful function out of it. Okay, so but we do that by the same kind of ideas and principles that we have in the physical world, like in the mechanics world and any kind of other world, where we have things like valves, things that turn things on and off, things to reduce certain things to reduce pressure, things to increase pressure. You know, we just call that voltage in electronics. We don't call that, flow of fluids and all that kind of thing, or, and all that, like dynamic fluid mechanics and all that. But it's the same kind of idea. Same kind of idea here. So a diode lets energy pass, or the current or voltage pass in one direction and not the other. When you see a diode, hold on, let's see this. Where are they found? Usually found in power supplies. And can we see why? Again, because it lets energy pass one way and not the other. Usually found in power supplies. What are they used for? Use for AC to DC conversion. I'm going to put here rectification. rectification. Okay. Why? Because that's usually what it's called. It's usually called rectification, but rectification, you can just say, is a fancy word for conversion. Okay. Rectification basically just when you say, oh, if we have to rectify this voltage, I'm changing it to AC to DC. If I was changing it from DC to AC, I'd say that I was inverting it. Okay, that's what our inverters are. Inverters became very popular the last couple of years, the last maybe 10, 15 years, because of advancements in IGBT technology and transistors, where we can make them more efficient, we can make them smaller and all these things. So inverter technology has come a long way. But the opposite of inverter is a rectifier, which is like an adapter. An adapter isn't a rectifier. Okay, so as you get more familiar with electronics, you'll start looking at those things differently, like a rectifier instead of an adapter. That's what it is. An adapter, again, that doesn't really exist in electronics language. That's just that's like a euphemism that we give these objects for people to use them in every day. But in electronics, that's called a rectifier. That's what that is. It takes AC signal out of the wall and it changes it to DC signal. Okay. So that's the primary use. Now, there's other uses for a diode. There are. We're not going to go into them. I just want you to know the basic usage of a diode, and that's the block. It can let current go one way, not the other. They're usually found in power supplies, and the reason why they're found in power supplies is to make AC signal convert to DC signal. Now we have the transistor. The transistor should be our most exciting component here. And forgive me, I'm losing space here. I'll just have to try to make this work. If not, I can just make another box on the bottom. I actually probably will do that just because I know I'll probably run out of space here. So the transistor. Again, like I said earlier, a transistor is basically a switch. Or I'm sorry, it's basically a two diodes that are put together. Its primary function, one of its primary functions is used as a switch. Okay. So a transistor is like an electrical switch. That's what you can think about. Because, and I know someone might come in here and say that has a little experience with electronics and has been around. I mean, if you've lived long enough, obviously, then you've worked on things, or you have, like everybody has a car, right? And you've heard of relays, right? What's a relay? Well, you could say a relay is an electrical switch, but that's kind of wrong. It's really a mechanical switch because it's just using electronics to move a mechanical switch. Okay, so relays aren't actually, now they have semiconductor relays. That's a thing now. Semiconductor relays, which is actually more of an electronic thing. But relays are used in electronics. They would fit more into the category of electronics than mechanical, yes. But what a relay does is it takes the voltage that's applied to a coil that moves basically like some kind of magnetic switch that then completes the circuit. But it's mechanical, okay? It's mechanical. Just like the switch on your wall. A transistor is not mechanical. It's completely a switch just by virtue of how you set up the voltage in it. And I'll show you why here. The next one will be turned on by 0.7 volts. Okay, so that's the magic number. So if you want to look at this as a switch, we can use our kind of language for a switch. A switch can be normally open or normally closed. A transistor, we can say, is normally closed unless you apply 0.7 volts to a certain region of it, and that will cause it to conduct. That will cause the electrons to want to flow into another region of it and complete the circuit. That's how you can use the transistor as a switch. Okay? Let me repeat that again so you guys can understand that. This is important. Using a transistor as a switch, you can apply 0.7 volts. Anything below that, it will be closed. Once you apply that voltage, the transistor will then conduct. It will then let the electrons flow and complete the circuit. That is how a transistor is used as a switch. That's not all transistors are used for. There's about 3 primary considerations I'm going to put in here for the uses of a transistor. First one is to be used as a switch. The second one is for amplification. I'm getting cut off over here. Okay, it can be used for amplification. And we won't go into too much of that, but just know that that's the second use of it, the second primary use of it. So this is why going through circuits, it takes a little bit of deciphering, because a transistor can be used for many different functions. That's why we have so much electronics today. After the invention of the transistor, it's like, okay, well, we can do a lot now, right? Because it can be used for various things, and it's not obvious what it's used for in a circuit unless you have some knowledge or experience into reading different schematics and seeing how circuitry is set up. That's why I want to show you in this next video common ways that some of these items, these primary components are set up, so you can get familiar with what does the schematic look like when a transistor is being used as a circuit or as a switch, as opposed to a transistor being used as an amplifier. Okay, you should be able to distinguish that, and I'll kind of show you some examples of how you could detail that, so how you would know and distinguish between the two. So the second one, or the third one, the third way a transistor is used is as a current source. Okay? The third way is as a current source. What do I mean by a current source? Sometimes in a circuit, you might have some losses in current, and you want to pull more current to a certain place because you want to drive something. So what happens is you put a transistor there, and the transistor will help you accumulate more current from the previous stage. So you can use a transistor to pull more current. You can also use a resistor, and you might use the resistor in conjunction with a transistor to pull that current. Because you have to remember, these items also have an internal resistance as well. See, a resistor also has internal resistance, and it has internal capacitance. So that's how these things work. None of these things aren't working usually alone, right? There's usually these other factors go into them as well. But that's the primary ways that a transistor is used: as a switch, as an amplifier, and as a current source. And in my next video, we'll talk about, I'll give you examples of what a schematic looks like when a transistor is used as a switch, what a schematic looks like when a transistor is used as an amplifier, and what does it look like when you use it as a current source. Or even better, after watching this video, you can do some of your own research in heat of you wanting to learn this stuff on different transistor schematics and look up for yourself, how is a transistor used as a switch? Get a schematic of how a transistor is used as an amplifier, and then get another schematic of how a transistor is used as a current source. And compare all 3 of them and see how they're different, see how they're alike. Hopefully you can find some schematics with a little brief explanation or synopsis, and that'll help you understand these things and get not only understand them, but start to develop a mental picture, an idea, and to where you can start committing this stuff to memory and have an understanding of this stuff. So next time we look over some schematics, you can pick out what the operation of that transistor is. Is it a current source? Is it an amplifier? Is it usually being used as a switch, etc.? All right. So those are basic 6 components for electronics. We have the resistor, the capacitor, polarized, non-polarized. We have the diode and the transistor. Again, I appreciate you guys for watching. Continue your electronics journey. I'm glad to be with you as you're going through it, and we'll just keep on with these videos. The next one will be more about networks and how to use these components. Have a good one.